In late 2030, we will know if there is life or not on Proxima b. Imagine yourself in the breathtaking Atacama Desert of Chile. The air is dry and clear, and the night sky unveils a dazzling display of stars and nebulae visible to the naked eye. Then, atop the Cerro Armazones, standing tall at 3,046 meters, or about 10,000 feet above sea level, you notice the pitch-black silhouette of what will become humanity's largest eye fixed on the cosmos, the Extremely Large Telescope, the ELT. The name might sound a bit cartoonish, almost like something from Mel Brooks' Spaceballs. Remember the scene with Ludicrous Speed? But it actually belongs to a colossal machine that is set to unlock incredible mysteries about our universe. Here's a little-known fact. Despite its massive proportions, the ELT is, in a way, a compromise. Back in the fall of 2005, a panel of experts convened to assess the feasibility of the OWL, an acronym for Overwhelmingly Large Telescope. And what a groundbreaking project it was! With a primary mirror spanning 100 meters or 328 feet in diameter, divided into 3,048 segments, OWL promised a resolution of 0.005 seconds of arc, 40 times sharper than the best resolutions achieved by the Hubble Space Telescope. But such a monstrous creation posed not only engineering challenges, but insurmountable economic ones, with the committee ultimately deciding to forgo. At an estimated cost of £1 billion 2 decades ago, the price tag was deemed far too steep. In response, the European Southern Observatory, the ESO, shifted its focus to the ELT. Still an ambitious endeavor, but one deemed technically and financially more viable. Even so, it will stand as the world's largest telescope, offering the scientific community unprecedented opportunities for exploration. In short, while the ESO abandoned the overwhelmingly large concept, they settled for a telescope that's simply extremely large, an acceptable trade-off. But the real headline is something else entirely. A recent study reviewed the ELT's technical parameters and simulated an observation of the atmosphere of the exoplanet Proxima b. The results? Once the ELT becomes fully operational, expected around 2029-2030, it will be able to determine within mere hours whether life exists on that distant world. Curious to find out how it'll do this? Keep watching this phenomenal video brought to you, as always, by the Insane Curiosity channel. No, this isn't just another telescope that's slightly bigger than the rest. The ELT represents a quantum leap in our ability to observe the universe. And nearly 1,000 square meters, or about 10,800 square feet of surface area, roughly the size of a basketball court, it will capture more light than any telescope in history, surpassing its predecessors by an entire order of magnitude. To put its scale into perspective, imagine current telescopes allowing us to see an open book from 1 kilometer, or about 0.62 miles away. The ELT, it'll let us read the text on the page. To better understand the groundbreaking nature of this behemoth, let's compare it to today's champions of terrestrial astronomy. Currently, the largest operational optical telescopes in the world are the twin Keck telescopes in Hawaii, with 10-meter or 33-foot primary mirrors, the Gran Telescopio Canarias in the Canary Islands, boasting a 10.4-meter or 34-foot mirror, and Chile's very large telescope, the VLT, composed of 4 telescopes, each with an 8.2-meter or 27-foot mirror. Even recent giants like Arizona's Large Binocular Telescope, which combines 2 8.4-meter or 27.6-foot mirrors for an equivalent 11.8-meter or 39-foot mirror, pale in comparison. The construction of the ELT is a colossal undertaking. Just consider its rotating opening dome. It will have an 85-meter or 279-foot diameter, stand almost as tall, and cover an area comparable to a football field, all while weighing in at around 5,000 tons. Inside, its vast volume of nearly 1 million cubic meters, or about 35 million cubic feet, will be maintained by an air conditioning and filtration system, creating clean room-like conditions. Dust, after all, is a telescope's mortal enemy. Moreover, the initial temperature must never deviate by more than 2 degrees Celsius or 3.6 degrees Fahrenheit from the cool outdoor night temperature at the moment when the sliding panels open. Supporting the telescope is a labyrinth network of metal tubes weighing over 3,000 tons. This intricate, mobile structure must ensure micrometric adjustments to the mirror's positioning, with precision down to just a few microns, while remaining stable and seismic resistant. Given Chile's reputation for not just crystal clear skies, but also some of the most powerful earthquakes on Earth, advanced anti-seismic technologies will be indispensable. The ELT's primary mirror won't be a single piece, of course. Instead, it will consist of 798 hexagonal segments, each 1.4 meters or 4.6 feet across, and just 50 millimeters or 2 inches thick. The secondary mirror, at 4 meters or 13 feet in diameter, will be as large as the primary mirrors of top-tier telescopes. The tertiary mirror will measure 3.75 meters or 12.3 feet across, and the ELT will also feature 2 additional secondary mirrors, making it a total of 5. This extraordinary telescope's primary mirror will boast a surface area roughly 14 times that of the Gran Telescopio Canarias. It's like upgrading from a modest window to a glass wall covering the entire front of a building. And in astronomy, bigger means one crucial thing: more light collected. But a massive mirror alone isn't enough. The ELT will also employ cutting-edge adaptive optics to counteract the distortions caused by Earth's atmosphere. This system relies on computer-controlled deformable mirrors that adjust thousands of times per second, compensating for atmospheric turbulence and delivering images as sharp as if the telescope were operating in space. Under ideal conditions, the ELT will achieve an angular resolution of 0.005 arcseconds, which means it can distinguish 2 light sources separated by 1 AU, the distance between the Earth and the Sun, at 650 light-years away, or 2 light sources 30 centimeters or 12 inches apart from a distance of approximately 12,000 kilometers, or 7,500 miles. For comparison, the unaided human eye has an angular resolution of 1 arc-minute, which equates to distinguishing 2 light sources 30 centimeters or 12 inches apart from just 1 kilometer or 0.62 miles away. Adding to its exceptional capability is its location, the Atacama Desert in Chile. Known as one of the driest places on Earth, it boasts over 320 clear nights per year and an incredibly stable atmosphere. Combined with the mountain's altitude, these conditions minimize atmospheric interference, providing an optimal setting for astronomical observations. But practically speaking, what does gathering more light actually achieve? The answer, while somewhat straightforward, is pivotal. In astronomy, a telescope's ability to observe faint objects is directly proportional to the area of its primary mirror. Light from celestial objects, especially the farthest or intrinsically dimmest ones, is extremely faint. Every photon counts, and a larger mirror simply collects more of them. To quantify this, astronomers use the concept of limiting magnitude, which describes the faintest object a telescope can detect. This scale is logarithmic and inverse. Each increase of 1 magnitude corresponds to a decrease in brightness by 2.512 times. For example, an object with a magnitude of 20 is 100 times fainter than one with a magnitude of 15. The naked eye, under ideal conditions, can see stars with magnitudes up to 6 or 6.5. A 50mm binocular can reach magnitudes of 10. Medium-sized amateur telescopes, 20 to 30 centimeter mirrors, can detect magnitudes of 14 to 15. The Hubble Space Telescope can capture objects with magnitudes of up to 31.5 through extremely long exposures lasting several days. Modern ground-based telescopes, such as the VLT, can achieve magnitudes up to 27 under optimal conditions and with prolonged exposures. However, the ELT, with its unprecedented light-gathering capability, will push beyond magnitude 30, approaching Hubble's capabilities while surpassing it in spatial resolution, thanks to its larger diameter and advanced adaptive optics. To put this into perspective, an object with a magnitude of 30 is about 4 billion times fainter than what the human eye can perceive. For instance, this sensitivity would allow the ELT to detect the light emitted by a single candle from 80,000 kilometers or about 50,000 miles away. Such extraordinary sensitivity will enable astronomers to study extremely faint phenomena, like the first galaxies formed after the Big Bang, exoplanets, and even the light reflected by their atmospheres. Another way to grasp the ELT's power is by considering exposure time. What a current telescope might take an entire night to observe, the ELT could achieve in mere minutes. Alternatively, in a single night, the ELT could collect far more detailed and higher quality data. It's like upgrading from a 1990s camera to the latest smartphone with professional-grade photography capabilities. Hey guys, just a moment before we continue. Be sure to join the Insane Curiosity channel. Click on the bell, you'll help us to make products of even higher quality. Additionally, the ELT sensitivity will be greatly enhanced by its specialized instruments, meticulously designed to maximize the light it collects. High-resolution spectrographs will break light into incredibly detailed wavelengths, allowing for precise analysis of the chemical composition of distant objects like never before. Advanced coronagraphs will block out starlight to reveal faint planets orbiting around them. Near and mid-infrared cameras will penetrate dust clouds, which are otherwise opaque to visible light, exposing stellar nurseries and galactic cores. One of the ELT's most powerful and thrilling features, however, will be its ability to capture faint atmospheric spectra from exoplanet atmospheres. This typically happens during a planet's transit across its star from our viewpoint. A small amount of starlight passes through the planet's atmosphere before reaching us. By analyzing absorption spectra, we can identify molecules in the planet's atmosphere, such as water, carbon dioxide, and oxygen. The James Webb Space Telescope, the JWST for instance, has already gathered data on several exoplanet atmospheres, yet transit data can sometimes be inconclusive. For example, when the JWST studied the TRAPPIST-1 system, planets B and C appeared to lack atmospheres, but the data wasn't robust enough to rule out thin atmospheres with spectral lines too faint for JWST to detect. Put simply, until now, we've lacked the technology to directly study an exoplanet's atmosphere for biomarkers, those chemical signs hinting at biological processes. Current telescopes, whether ground-based or space-based, aren't powerful enough for this monumental task. The ideal solution would be an instrument capable of continuous observation, tracking changes over time. Prolonged observations, which JWST cannot offer, as 95% of its time is committed to cosmological studies, are essential for determining whether faint signals suggest a stable, active atmosphere or are merely transient phenomena. And this is where the 39-meter, 128-foot telescope shines. Its prime location in Chile's Atacama Desert offers incredibly favorable observation conditions: dry air, minimal atmospheric humidity, and unparalleled sky transparency reduce interference to nearly zero, unlike telescopes situated in less optimal environments. With its ability to produce images 16 times sharper than Hubble's, coupled with advanced instruments specifically designed to block starlight and examine the planets around them, the ELT will finally provide an up-close look at Proxima b and countless other potentially habitable worlds. What's even more exciting is that the ELT could gather spectra not only from exoplanets transiting their stars, but also from non-transiting ones through reflected starlight. To illustrate the ELT's immense potential, a recent study simulated results across various scenarios. The study's authors focused on planets orbiting nearby red dwarf stars, the most common type of exoplanets, examining 4 test cases: a non-industrial Earth teeming with water and photosynthesizing planets, an early Archean Earth where life is beginning to emerge, an Earth-like world with evaporated oceans similar to Mars or Venus, and a pre-biotic Earth capable of supporting life but without any. For comparison, they also included Neptune-sized worlds with substantially thicker atmospheres. The primary aim was to assess whether the ELT could reliably differentiate between these Earth-like cases and crucially avoid false positives or negatives. For example, mistakenly interpreting a lifeless world as habitable or dismissing a living world as barren. The simulation results were promising. For nearby star systems, the ELT is expected to deliver clear, accurate distinctions. For Proxima Centauri, our closest stellar neighbor, the ELT could detect signs of life on an Earth-like planet in just 10 hours of observation. For larger Neptune-sized planets, it could achieve spectral readings within an hour. With its highly advanced adaptive optics virtually eliminating atmospheric distortions, the ELT will be able to analyze critical spectral signatures, such as the absorption lines of oxygen and methane, with such precision that it can distinguish between signals of biological origin and those arising from inorganic reactions. Combining this capability with real-time atmospheric monitoring, observing fluctuations in temperature, pressure, and gas composition will provide something akin to a snapshot of a distant planet's environment. This in turn allows us to assess whether its conditions are stable and potentially conducive for life. While the search for life on Proxima b and other nearby planets is undoubtedly one of the ELT's most exciting goals, its impact extends far beyond exoplanetary exploration. This colossal scientific instrument promises to revolutionize nearly every domain of knowledge, including our understanding of ourselves. Because yes, the discoveries made by the ELT could be so transformative that they reshape how we view our existence as a species. Should we uncover evidence that life, from the simplest forms to more complex organisms, is not rare in the universe, our worldview will expand in ways we can scarcely imagine. And this shift will occur even if we never physically interact with those distant worlds. The best part? Unlike many other astronomical projects that take decades to materialize, the ELT is set to begin operations remarkably soon. Its first light is slated for 2029. Following this milestone, the telescope will enter a phase of optimization and calibration, during which its initial scientific instruments will be installed and rigorously tested to ensure harmonious and high-quality data collection. This preparatory phase is essential for enabling official scientific observations to commence in December of 2030. So we just need to hold on a little longer and make sure nobody dares to miss it, because soon we will find out whether light or shadow will fall on our hopes of knowing that life is spread everywhere.